second part of the class of today, which is basically the main topic of the new topic of this lecture, which is the constitutive equations. We will see that an additional complication of the theory of curved beams arises from the constitutive equation. So we can have additional complications. We have geometric couplings between the quantities that we have seen here. So we have couplings between the axial strain and transverse displacements. We have couplings between shear forces and axial force and transverse load and axial forces. Those are geometric couplings. We can have also, due to those couplings, the couplings that we have discussed so far. Yes, you can hear me. Yes. The couplings that we have discussed so far are geometric origin, are due to the fact that the axis line has a curvature and a torsion. Now we will see that an additional coupling can arise from the constitutive equation, so from the relationship between stresses and strains. So at the first approximation, we can ignore this other coupling, this constitutive coupling between stresses and strain. So at the first approximation, if the curvature of the axis line is not extremely strong, so which corresponds to the case in which the ratios between the height of the beam and the radius of curvature, the radius of torsion, are in the range of 1/50, 1/100. If we are in this range of values of curvature and torsion of the axis line, we can basically ignore the coupling in terms of constitutive equations, and we can assume for the curved beam the same constitutive equations that are assumed for the straight beam. You see some coupling terms here due to the fact that we are writing these constitutive equations with respect to axes that are not necessarily coincident with the principal axis of inertia of the cross section. So the couplings that you see here are just due to the fact that we are not assuming that the x1, x2, x3 are the principal axis of inertia of the cross section. So those couplings are also present in the straight beam. Why we are not assuming that these axes are necessarily coincident with the principal axis of inertia? So we have basically this mixed inertial moment I1, I2 that is not present if the axis 1 and 2 are principal axis of inertia. We have this inertia product E1, 2 equal to 0. We are not assuming that because we are assuming as a triplet, as a triad to which we refer our equations, the Frenet triplet. So the tangent vector, the principal normal vector, and the binormal vector. And so these three vectors are associated with the axis line. So are associated with the fact that the axis line has a curvature or maybe as a torsion space. But we are not forced to let the x1 and x2 axis coincident with the principal axis of inertia. When we choose a cross section of a curved beam, we are not forced, we are not obliged to assume that the cross section has the symmetry axis or the principal axis of inertia coincident with the normal and the binormal. So for this reason, we have kept in our constitutive equations of the classical beam theory the coupling term due to the fact that we are not assuming a principal axis of inertia for our. So in most cases, those the principal axis of inertia coincides with the normal and the binormal. So the I1, 2, I1, 2 will be 0, and those equations will be the same as the equations of the classical equations of the straight beam. And also, for the same reason, we have coupling terms between the two shear forces with the coupling shear factor T1, 2, and also this other one coupling can be set to 0 if one of the two axes is a symmetry axis. This is the same as in the straight beam. So you can see now that we don't have in these equations, we are not assuming a coupling between, in terms of constitutive equation, between the bending moments and the axial strain. So the axial strain is only related to the axial force, okay? Because we are directly applying the results, we are extrapolating the results for the straight beam to the curved beam. And so we don't have a constitutive, we don't have a coupling between different components of stresses and strains due to the curvature of the beam. Now, and this is what we can do, what has been done we can also assume that the third equation will add the moment MT, the torsion moment computed with respect to the shear center of the cross section, and so as in the classical beam theory of the straight beam theory. And so by extrapolating the constitutive equations of the straight beam to the curved beam, we have this, we can assume these relations. And we can also get the expression of the strain energy, which is given by the integral of the generalized stress times the generalized strains, the line integral over the axis line, alpha 1 over 2, and we obtain the same expression of the straight beam. So, having added to the equilibrium equations and compatibility equations, which are the relations that define the generalized strains in terms of displacements, having added the constitutive equations, we can present the boundary value problem. So the problem for we will see through examples in the. So this is just the cross section of the beam with the inertia axis, and we are also showing the center, the shear center T. So the boundary value problem is formed by the equilibrium equations. Now we are using the more engineering notation, in the engineering notation, which the components of nu and mu are named T1, T2, and N instead of N, nu1, nu2, and nu3. And also for the components mu, we have M1, M2, and M3. And these are the same equations that we have seen before in engineering notation. So these are the equilibrium equations with the couplings, the geometric couplings that we have discussed before. You see here that in the equation with Q2, we have this n over rho. And so with this coupling and all the equations that are geometric coupling between the generalized stresses. The constitutive equations have only are the same as to a first approximation, are assuming the same. So here we have, but in these equations we have actually we have mixed the compatibility equations and the constitutive equations, because those equations we have the generalized strains that are defined in terms of displacement. So we have these are constitutive equations and compatibility equations, assuming extrapolating the straight beam theory to curved beams, and we have the usual natural and forced boundary conditions. But this will be so. I could quit here my lecture, which I would be happy to do, but this is not possible because this, unfortunately or luckily, because those couplings are beneficial in most cases. Those equations that we have presented before are not exactly valid for beams with strong curvature. See, if you have a beam which has a strong curvature, we cannot use the constitutive equations that we have seen so far. So what we can do? We have to obtain constitutive equations that account for the final curvature of the beam. So what we can do? This is more involved, and so we have to obtain from scratch the constitutive equations of the curvature. We cannot extrapolate them from the theory of the straight beam. Again, we have the position vector is of the generic point is obtained by summating to X, which is the position vector of the centroid, vector R, which is given by x1 e1 plus x2 e2. And we obtain the expression epsilon 3 that we have already shown before. So this equation has already been obtained. This is the component of the epsilon 3. Why do we need to have epsilon 3? We will see in a while. So this is the exact expression of epsilon 3 that we have already seen earlier when we have analyzed the expression of the infinitesimal strain tensor for the curve. So we have this J factor in front of the expression of the same expression that is customary for straight beams. So this is epsilon 3. And now this epsilon 3 accounts for curvature, because the exact expression of epsilon 3. So this is definitely the epsilon 3, the final expression of the epsilon 3 that is obtained by carrying the derivatives of vector v, phi, and also the derivatives in one and two that account for Premi formula. So this is the final expression of epsilon 3. As you see, in the end, is not dramatically different from that of the straight beam, because in the straight beam, this J is equal to 1, which is the Jacobian of the transformation from curvilinear coordinates to Cartesian coordinates. In the straight beam, you use Cartesian coordinates, you don't need this Jacobian, which is 1. In this case, you have J is not 1. And obviously also the difference is symbolic. This equation is similar to that of the straight beams, but we should account for the fact that this expression of epsilon, of theta 1, theta 2, which are what we call the epsilon 3, epsilon 4, and epsilon 5 before, when we defined the generalized strings, obviously inside in the definition of epsilon 3, epsilon 4, epsilon 5, which is here, it's not here, we have terms that account for the curvature and the torsion. But incorporating this effect of curvature and torsion in the expression of these generalized strains, we have the final formula for the epsilon 3 is the same as that of the straight beam with this 1 over j inverse. Now, what we do now is this. We assume that to obtain the new constitutive equations for the curved beam, we assume a local constitutive equation for the continuum medium. So we assume that the sigma 3, the normal stress, is proportional to the axial strain epsilon 3 through the Young modulus E. This is, this can be justified in several ways. One, why we are assuming the sigma 3 is equal to E epsilon 3. The first justification is that we can assume that the material of the beam is isotropic with a Poisson ratio equal to 0, and this is the first way of justifying this assumption, because in a three-dimensional body, the Poisson effect couples the axial strain in one direction with the axial strain in the other direction. If you stretch a piece of material in one direction, it will be stretched also in the other direction. This is the Poisson. But in the beam theory, we have to ignore the Poisson effect because of we have assumed the cross section remains rigid. So this was our basic assumption. So in order to introduce the constitutive equation to respect our assumption that the rigidity of the cross section into the constitutive equations, we have necessarily to assume that our material has we have to force the Poisson coefficient of the material of the beam to be 0. So this is one way of doing of justifying this expression, this assumption, which is also done in the theory of the straight beam. It's exactly the same assumptions also introduced in the theory of the straight beam. Another way of justifying this assumption is that you have the material of the beam is not isotropic, is transversally isotropic, and has infinite elastic moduli in the transverse directions. We could always to account for our assumption of the rigidity of the cross section. In one way or another, we can assume the sigma 3 is equal to E epsilon 3, and this is respectful of the assumption that the cross section remains rigid. And so we assume this equation. Now it's just a starting point of a cumbersome process, because obviously what we are generalizing here are the constitutive equations related to the axial forces and the bending moments. We are not generalizing the other constitutive equations that we assume coincident with those but those are the most important equations to be corrected. So this is the equation that we will use. Now we know that N, this axial force and the bending moments, are given by the integral of sigma 3, and the first moment of moment sigma 3 x2 and sigma 3 x1. So if we carry out these integrals, we obtain for sigma 3, we use this expression that accounts for the curvature because j is not equal to 1, and we insert this expression sigma 3 into the definition of generalized stresses. And so we have now, if we account for j, which is 1 minus x2 over rho, we obtain this equation. Now, what is the problem? What is the problem? Is that if we carry out this integral, if this quantity would be 1, if this j is 1, if you carry out this integral, what do you obtain? You obtain only the term with epsilon, okay? Because the other two integrals will be the integral of x2 and the integral of x1. Usually we take, we have assumed that the origin of our local coordinate system is at the centroid of the cross section. So the integral of x1, the integral of x2 are the static moment of the cross section will be 0. Now we don't have this result. So this integral, the integral of x2 divided by j is not 0, and the integral of x1 divided by j is not 0. So this means that we will have n also at the constitutive level related to theta 1 to the bending strains, because j. So we go back to the previous theory. If j is approximatively equal to 1, so when the x2 over rho is a quantity that's almost 0. x2 over rho. What is x2 over rho? x2 is the coordinate in the plane, the component of r along the E2 axis, and x1 is the component of r along the E1 axis. And rho is the radius of curvature of this line. So when x2 over rho, when this can be taken as 0, when rho, when the center of curvature is very at a high distance from the centroid of the cross section. So when the radius of curvature is very large, this x2 over rho will be almost 0, because we are taking x2, which has the dimension of the height or the diameter of the cross section in the mathematical sense, divided by a radius that is 100 times, maybe larger than the height of the cross section. And so this quantity would be 100 with 0.01. So 1 divided 1 plus 0.01 is almost 1, and we can neglect this cap. But in the general case, this is not true. So now we will account for this coupling. And so if we expand, we have to introduce some quantities that are slightly different from those introduced for the straight. So we can introduce these quantities are defined below. We can introduce the reduced area. Let's start from the first, from the reduced area, which is rho divided rho minus basically 1 over j, the integral of the sigma. This will be the area of the cross section if j is equal to 1. Why? It will be different from the area of the cross section if j is not equal to 1. In order to get a more clear expression of this quantity, let's start with A. a rho, so it's the area of reduced area, reduced area of the cross-section, an area that carries into its expression the curvature of the axis line. So we can write the integral rho divided rho minus x2 as simply by a trick. We add and subtract x2 at the numerator. Then what we can write? Rho minus x2, we divide rho minus x2 gives 1. And then we have plus x2 over rho minus x2 as an additional term. So this other quantity, this is the area. This other quantity is what we call the reduced static moment with respect to the axis, the axis 1. So the integral of x2 divided rho minus x2. This quantity we call S1 rho. So basically, actually, S1 rho is x2 multiplied rho, the factor rho times rho minus x2. And so if we call this the reduced static moment of inertia, which is, you can demonstrate that this is by a trick, again, we can do x2 rho minus x2 plus x2 squared. This is the reduced static moment is just the reduced inertia moment, we define it this way, divided by. So the area, reduced area, is equal to the area affected the actual area of the cross section plus J1 rho over rho squared. And this is J1 rho, S1 rho. Then we have also J2 rho, J12 rho, which is not zero, even if the axes are principal, are axis of inertia, principal axis of inertia, because this quantity x1, x2 is multiplied by this factor. And then we have S2 rho, which is equal to J12 rho over rho. So we have defined a reduced area, reduced static moments or reduced first moment of area, reduced moment of inertia or reduced second moment of area, using the English notation, and reduced product moment of inertia or product moment of area, which is the J12 rho. So we have this quantity with the rho index that account for the curvature of the axis line. And so x2, x2 are measured from the centroid, but the other, this S1 rho and S2 rho are not zero, while S1 and S2 are zero. So in the end, we end up with this constitutive equation, so which are rather cumbersome, and is equal to EA epsilon, which is the classical term, plus one term that is related to the reduced moment of inertia. Then we have a coupled term with θ1 and θ2 in the constitutive equation. And this J1 rho and J12 rho are the quantities defined above. Okay. Now, if rho is large, what is J1 rho is equal to J1? Because if rho is infinity, if this is 1, this term is 1. Okay? S1 rho is 0. A1 rho divided becomes area. J rho becomes the J2. J12 becomes 0 if we are taking the principal moment inertia, and also S2 becomes 0. But generally speaking, those quantities are not zero. So we have this coupling. You see these two couplings. We have this J1 rho and J2 rho. Assume that rho goes to infinity. This becomes the standard moment of inertia. But then we have a rho. A rho, if rho goes to infinity, those coupling terms goes to 0. M1 is related to epsilon and also to theta1, which is the classical term. And also you have these two. This other coupling is due to the fact that we are assuming that the principal moment of inertia and principal axis of inertia are not necessarily E1 and E2. This is the same coupling we have in a straight beam theory before. While these terms, this coupling term with epsilon is due to the curvature. Also here we have these terms that are standard, and we have another term, this coupling term, this is related to curvature. So, inverting those equations, which is not an easy task, we have epsilon is equal to n or EA minus M1 over rho EA. And this quantity can also, this equation can also be expressed in the term epsilon equal to NR over EA. If we define NR as N minus M1 over rho, which is the reduced axial force, we could write this equation in the standard form. But if we don't introduce this quantity, we observe this coupling term. We have the analogous coupling term appears in theta1 and then theta2. The other coupling terms are the same as in the straight beam theory when the axis 1 and 2 are not principal axis of inertia. Those are the couplings that are important to us, are these terms. And also, you see this other, there is also the stiffness, the bending stiffness changes, because if the beam has a strong curvature, you have the bending stiffness has also terms that is proportional to the area of the cross section. And if we want to obtain the analogous of the Navier formula for the sigma 3,3, so we want now to express the sigma 3,3 in terms of the stress resultants. We have this cumbersome equation. Sigma 3,3 is not equal to NA plus M1 over I1 X2 minus M2 over I2 X1, but there is this cumbersome Navier formula, cumbersome generalization of the Navier. Fortunately, in most cases, we can assume that the cross-section is a simpler expression. So we can assume that the cross-section is a normal domain with respect to the x2 axis. The x2 axis is when you draw the cross-section is the vertical axis. Okay, is this one. We can assume that this basically the contour of the cross section can be defined as a domain that is normal to this axis, which means that you can assume that the coordinate x2 goes from some bounds, is a contained given bounds. This is the assumption. So x2 varies between some bounds, and we can have more bounds because the session can be multiply connected, so we can have holes in our sections, in our cross section. But if we have only one simply connected section, we will have only one of those inequalities. And then the x1 varies between two curves that are parameterized as a function of x2. So those are basically the normal domains. So domains like this one. Yeah. Sorry for the people who are not here.
Ma tolgo la condivisione dello schermo così.
So if we assume that x2 goes from then something like that. So this is what we are assuming. if the section is a normal domain with respect to the x2 axis, so we can assume this expression, this shape. So the x2 varies between two bounds, and the x1 varies between two curves that are defined as a function of x2, which is the definition of a normal domain with respect to the x2 axis. I will share. I will just try to not collapse myself over the platform because I want to enjoy my final days in Cagliari. I want to enjoy Cagliari for another couple of days. So, if we assume this assumption, which is true for most of the cross sections that are used in practice, then the J12, this J12 goes to 0 because we can show that this is true. So the J12 and S2 goes to 0. At this point, this is the equation, this is the shape with this assumption, this simplification. The n is equal to the constitutive equation for n is this one, more simple. We have, as we can see, we have a term, and we have two terms, coupling terms related to the curvature. One is the first order coupling term, and another is the second order coupling term, because this goes to 0 faster than the other one, because this goes to 0 when rho goes to infinity, this goes to 0 with more quickly when rho goes to 0, when rho goes to infinity, 1 over rho goes to 0. And we have this coupling. We have also this coupling terms in M1 and M2. And if we invert, we have epsilon equal to 1 over EAN minus M1 over rho, theta 1 equal to N minus this equation that shows the coupling between the curvature. This term disappears if the curvature goes to 0, so the radius curvature goes to infinity, and theta 2 is given by this more simple expression. So the generalization, okay, this is our internal comments. Okay, so this is the, okay, I will try to hide this. These other are from vabbè, non mi ricordo come si fa. So this is the generalized Navier formula, in which looks like the formula, but not really the standard formula, not really, because we have these Jacobian terms here, and also here we don't have that real axial force, so we have this reduced axial force, which is just been defined here as n minus m1 over rho. And this is, so those are the constitutive equations, the generalized Navier formula for the beam with a strong curvature. So that this justifies why in our course we have named our course as a course of the mechanics, about the mechanics, mechanical modeling of curved and twisted beams, geometrically exact, because we can account for all the couplings in the equilibrium equations, into the compatibility equations, which are geometric and are of geometric nature, and also in the constitutive equation, which are also derived from geometric term, from geometric considerations, but are usually ignored in a normal curved beam theories. So we will see in some examples in the final days of the course that those couplings introduce some modifications of the solution and so we can have a first solution using the classical constitutive equations, or we can have another solutions that are account for the curvature of the strong curvature of the beam. Why should we use these coupling terms in the constitutive equations? Because we want to the curved beam theory can be useful for many purposes, not only for studying, for example, arches that are over form roofs of a building, of a civil engineering constructions. But we can use this theory also for studying some the stresses in some mechanical pieces, in some elementary other elements. For example, in hooks, if you want to study what is the stress distribution in a hook that use it for hanging loads, those would be a beam with a strong curvature. And so we need to use these correction terms in some limited cases, while normally in engineering, civil engineering applications, these coupling terms in the constitutive equations can be ignored or to a first approximation, because this h over rho and h over tau are basically quantities rather small and close to. Okay, this should close the program of today, because with respect, just ignoring this comment, we should now start with the planar beam case. I don't know if it is the case to start today, or we can postpone this to tomorrow. These concepts are not so but are very dense. So maybe we can postpone this to tomorrow and start today. They will also prefer Antonio. I guess if we ask the students, they will tell us to postpone to tomorrow. But so it should be our decision. We shouldn't ask them. I'm pretty sure that this what will be their answer. So this is more easy, because what we will present tomorrow, because it's just the simpler case in which tau is equal to infinity, or 1 over tau is equal to 0. So the classical curved beams, which are curved but in a plane. And so maybe we can postpone tomorrow. Okay. No. Okay, so we close a bit earlier, but I think that our program is dense, and we would like to ask you questions. If you have any questions, and otherwise we will ask you questions. No, just kidding. But so if you don't, so just consider this. If you don't ask us questions, sooner or later we will ask you questions. So it's
okay. In this case, I will ask you.
yes.
You introduced 3D shear correction factors.
Yeah, the coupling, yeah, P1,
How you introduce it?
yeah, this is from the just extrapolating the classical beam theory. So in the classical beam theory, not everybody does that, but if you derive the classical beam theory from the three-dimensional continuum, you can assume, for example, that the correction, we have to define way of correcting there are several approaches. It's an energetic approach. You can also use, for example, the Jurassic theory for the strain, for the stresses, and then you go to the tangential modulus analysis. You define the shear strain, then you integrate, and then you will have these correction factors in general if the axes are not axis of symmetry. So if you don't have any axis of symmetry, even in the classical and the straight beam theory, you have a coupling term between the two shear forces. Usually you have at least one axis of symmetry. So there's this is not a topic for our this course, because we are extrapolating those questions from the but this there are several ways of correcting the classical beam theory, accounting for working effects or for working effects.
Cross sections.
Yeah, but in the constitutive equation, usually what you do in engineering, so this is done by engineers. Okay, we are engineers. We are not pure mathematicians. So what an engineer does is that we use the theory that assumes that the cross sections are rigid, even when the cross sections are not rigid. And how do we do that? How do we play the trick? We correct the constitutive equations accounting for working. I know this is just an engineering trick, but this has been played for years, and so on. It's a trick. So you introduce some these correction factors. For example, one way of introducing correction factors, you want that your strain energy of the beam theory is the same as the exact strain energy of the beam, analyze it as a three-dimensional body. If you this is one way, this energetic way of defining this shear correction function. You put this two strain energy equal to each other, and you have this correction factor. So why should you do that? Because in this way, if you introduce this correction factor this way, you will have in the end that the energy associated to your theory will be the same of that of the unconstrained theory without this restraint the cross section remaining. But it's a trick. It's just a trick that
Okay, so
the engineers.
avoided questions for a while.
What?
So I personally avoided questions from you, from Professor Gattani, at least for a while. You can ask us.
Okay. So the engineers have always to find a solution, even if it is a approximate solution. So the mathematician would say, no, you cannot use this theory. If there are working effects, you cannot use the beam theory. And this would be the answer of a mathematician.
Then that's the wrong mathematicians. Because the problem was this approximation theory by definition.
Yeah.
So then proper question is a good approximation or not?
Okay. Okay, I don't want to answer for mathematicians, but for the engineers to do play tricks. The engineers play tricks, but usually these tricks work fine to some extent. So if you are in theory that if you are in a case in which these working effects, the fact that the cross section does not remain rigid, so there's some working, some fetching into the frame of the cross section. In most cases, with these corrective factors, in the end, you account for these effects, for example, in terms of energy.
I can add something.
This is my explanation. You can give yours. You can give yours.
My construction major teacher was from Naples. He was a very, very efficient professor, and he used to say that if you violate a agreement, you go to jail. That is not exactly correct because you see that you can destroy a bridge and go to jail.
Okay.
But in other cases, you are expected to go to jail if you violate. But if you violate compatibility or something like that,
It's also good answer.
if you violate the working or something like that, okay. From an energetic point of view, you are right. Why should you worry more about it? After all, what is very important is the quality of that person.
Yeah, I have never seen anyone using this mutual shear correction factor K1, 2, but if you want to be more exotic, you should add the K1, 2 if there is no axis of symmetry.
If one of the students say at home, that's exactly right.
But I think that nowadays, actually, this is true. Your question is meaningful because nowadays, this K1, 2, K2, we don't teach anywhere how you get this expression because usually when we analyze the shear, the Sandman problem and the correction to the Sandman problem, we use it in years ago to derive this expression, this K1, K2. Nowadays, we don't do that any longer. So these are really magic numbers.
So the standard,
But in
rectangular cross-section, how to develop the shear correction? At least for the rectangular cross.
but the K1, not the K1,
Yes.
the K1.
But also K2.
But K1 and K2, yes. K1 and K2 we still do, but the K1, 2, yes, it's in the book. But usually,
No, I don't see the idea because you told that this shear correction factor 3 appears for any of the arbitrary axes. So it means that if I consider, let's say, some symmetry axis, should be, it looks like the matrix. Maybe there is only two independent from them, and others should be conformal.
no, there is an expression. For example, if you have a section this as an S, there is an expression for K1, 2. There is a one K1, 2. I can give you an expression. It's a matter of definition. So what you define as a shear correction, because it's just a factor that should not appear in the theory. It's a correction to introduce, and you force the theory to be valid also when it's not valid.
For S, to a symmetry as cross-section, for example, rectangle.
Rectangle, yes, 0. K1, 2 is 0. K1 and K2 are not 1, but K1, 2 is 0. If you have one axis of symmetry, it's 0. You don't have one axis of symmetry in the general case. Okay, but this was for the student. So you should ask a question tomorrow. Be prepared to ask a question because otherwise we will ask you, or either you don't show up tomorrow. It's up to you. Okay. Thank you, Dan, and we will meet you tomorrow. But tomorrow is we have a class also in the morning. What time is there? 9. Okay. 9 with some shear correction.
Yes. And then another one is afternoon at 3.
3, as today. Okay. We will see you tomorrow then. Thank you. Thank you. Bye.
Thank you. Bye.
Thank you. Bye. Goodbye, everyone.
Bye.